Thank you, and thank you for coming. So what I want to talk about today is to, kind of show you what happens when you look at privacy and anonymity systems when you're a mathematician. Just sort of look at it with a graph eye and, give you sort of a little bit of a preview with that. All right, last row. Can you see my hand if it's at this height? Yep. Okay. Good. All right. So when people design anonymity systems, it seems like the leading paradigm right now is k-anonymity. Because it's kind of what we know how to do. And how it works, I know this is a mixed crowd, so just a really quick explanation of that. So we have a bunch of users of a system, right? And it's usually really expensive from the point of view of, fooling the infrastructure to make them all indistinguishable from one another. Because, we're talking about the internet, right? So the infrastructure is going to distinguish between them. So instead, we divide them up into groups and make them indistinguishable within those groups, because that's cheaper. All right, so if those groups are of size at least k, then that's k-anonymous. All right, so this is a 3-anonymous system. Now, the way people actually think about this is they sort of set up those groups as, kind of equivalence classes, right? They just cut up the set of users. They put them in one bag, another bag. If two users are in the same group, then we're trying to make them indistinguishable. But why is that? Why is that the thing to do? Is there some better way to do this? Well, we haven't really figured out, from the engineering point of view, how to do something else. But maybe, in theory, there is something that could be better. What do I even mean, right? Because when you sort of think about that as how else would you do it? Well, think about something like this. So you have Alice, Bob, Charlie, and David, right? And you're observing 4 different behaviors, right? And you're sort of you can see that one behavior could either belong to Alice or Bob. One of them could either belong to Bob and Charlie. The third could be either Charlie or David. And the fourth could either be Alice or David. All right, so that's not the same thing, because they're not cut up into, if we were talking, it could be so those are not equivalence classes as opposed to one behavior looking like that, the other one looking like that, the third one looking like this, and the fourth looking like this. All right? So can you see some sort of a reason why you would prefer one of those rather than the other? Just, Right. So can you just say what that is?
So the intersection attack is when you see, say, the Alice-Bob behavior, and then you see the Alice-David behavior, you take the intersection and you know it was Alice then.
Well, so suppose this is your entire picture, right? So you can't tell that this behavior belongs to the same person. Those two right? So you essentially see, you just sort of have a snapshot. You have 4 different things, and they belong to 4 different people. But that's essentially the information that you can filter out of it. Here's what I was thinking about. With this one, suppose you figure out that the first behavior belongs to Alice, right? Then you know that the 4th one has to belong to David. And then if you know that, then you know that the 2nd one has to belong to Bob, and the 3rd one has to belong to Charlie. Right? In this situation, if you figure out that the first behavior belongs to Alice, then you've de-anonymized Alice and Bob, but you don't know anything about David and Charlie. All right, so essentially what I'm saying is, here there are 2 ways to assign the 4 behaviors to the 4 users. Here there are actually 4. So if you figure out which one of the 2, like what's happening with Alice's behavior, you still have some information about David and Charlie. All right, let me put this on a different footing where it's going to be clear, right? So here's where we come to picturing this as a bipartite graph, right? So on one side, I'm going to put users. On the other side, I'm going to put behaviors. All right, so users, behaviors. All right, Alice, Bob, Charlie, David, 1, 2, 3, 4. So in this situation, behavior 1 could belong to either Alice or Bob. Behavior 2 could belong to either Bob or Charlie. 3 could belong to Charlie or David. And 4 could belong to David or Alice, right? And in this situation, it looks a little different. Right, so the first 2 behaviors are either Alice or Bob. And the 3 and 4, Charlie or David. Make sense? All right, so here, if you're looking for ways to assign behaviors to users, here, suppose you figure out this, well, then you know for sure that the rest has to go like that. Right? You only have 2 ways to do this. The alternative is like that, right? This is the only other way you could possibly do that. All right? And what happens if you figure out this part? You still have 2 options. Right? Those are perfect matchings in a bipartite graph, right? So a matching in the graph is essentially you put vertices of a graph in pairs, and those pairs have to be connected, right? And this graph is bipartite, which means that you have a set here and a set here, and there are only edges going from one to the other, right? And we want to match all users to some behaviors in a way that makes sense. All right, so I'm going to put some stuff on the board now just to make that clear. All right. So, this is not going to be the classic math definition. I'm just going to define it in terms of users and behaviors for this, for the sake of this application. So perfect matchings. Assignments of, well, I guess you could say bijection, that, if that's sort of closer to a language that makes sense to you. Assignment of the set of users to the set of behaviors. Right, this has sort of, the math version of this definition would be you have a bijection from this set to this set, and you can only assign something if there's an edge, right? So for graphs, right, so suppose this graph is set of users X, set of behaviors Y, and then bijection from one to the other in a way that, you can only send something to if, to the other thing if they're adjacent. So x adjacent to y. All right, now the fun part about this is that we know a whole lot about perfect matchings in bipartite graphs. And one of those things is, we know how to count them, right? So what I'm trying to do here is, we would like to show that this kind of situation has more of them than this one. So this one has 2. How many does this one have? Like ways of assigning users to behaviors? That's right. Why? Yeah, so essentially you can do this in 2 different ways, and you can do this in 2 different ways. So, and it's independent, right? So you're going to have 4 different ways of doing this, right? So this is not an entirely new idea. There was a paper published in 2007 that already said, if you count ways of assigning users to behaviors, that might say something about anonymity. And people looked at that paper and they immediately said, well, that's not a very good metric because, well, for the following reason. All right, so look at the following graph. All right, I'm going to have 7 users and 7 behaviors.
Can I just ask a question?
Yep.
Basic question, just stepping back a little bit. So when you said you actually want to know whether or not you can do better.
Yes. Oh, no, that's a very good question, actually. OK, so obviously I want to maximize the number of those matchings, right? But how do you like maximize based on what, right? So essentially, every time you make one user indistinguishable from another, that costs you something, right? So, and in this case, a good model for infrastructure cost is the number of edges, right? Because every time you put in a new edge, that's fooling the infrastructure in some way, right? So the question is, and I'm glad you pointed that out. I'm going to write it down in a second. The question is, based on, with respect to the number of edges, what's the maximum number of matchings? Like, what's the structure that gives you the maximum number of matchings? All right. Look at a graph like this. All right, this is how many matchings does this have? All right, so what about this part, right? This person can be assigned to any of these 3 behaviors, and then this one can be assigned to any of the remaining 2, right? And then this one has to take what's left, right? Here, just like over there, we have 2 different ways of assigning them, and here we also have 2 different ways. All right, so that's 24. All right, there's a problem with that. So look at this graph that also has 7 users and 7 behaviors. Is that 7? Yeah. All right, so we're going to do this. All right, so what just happened here? How many matchings? 24, right, because this is 4 factorial, right, the same way. And then these people just don't get anything, right? So this is a problem, right? You don't want to construct a system where like a bunch of people will not have any anonymity at all, right? So you could argue, well, this is not a very good metric, right? Because you have the same number of matchings, and this is clearly a better situation than that one. Well, here's the thing, though. If I can show that a model that is symmetric, that doesn't really leave people out like this, actually gives you a maximum number of matchings, then we're good, right? You're just, just get that number of matchings, and then you already have the symmetry, or the approximate symmetry. Make sense? All right. Fair enough. All right, so let's write that down, what the aim of this whole thing is. Okay, so aim. Show that a graph that corresponds to the k-anonymity model gives the same, optimizes the number of matching. For some number of edges, right? So for number of edges, I'm going to call that number m, and then I'm going to make k the floor of m over n, where n is the number of users. All right, so what just happened here is I have some number of users. I have some amount of edges that that can go around, right? And I want to show that if I actually distribute those edges more or less evenly as I can, right? Everyone gets at least the integer below m over n edges, and do the model like this, then that actually optimizes somehow the number of perfect matchings, right? Are there any questions so far? All right, I'm going to wipe this. All right, so this is where we get into a little bit more math. So if we want to, so suppose we have this kind of graph, right? Just make this an example. How do we actually, somehow like, quantify anything about this graph? Well, we take its adjacency matrix, right? We know adjacency matrices? Excellent. All right, so the adjacency matrix of this graph is you have, you're gonna have rows and columns that correspond to the vertices, and then you put a 1 in that spot if there's an edge, and a 0 if there isn't. All right, so 1 is adjacent to A, there's a 1. 1 is also adjacent to B, but not adjacent to C. And then 2 is not adjacent to A. And then 3 is not adjacent to B. All right, so that's the adjacency matrix. And then for the next step is something called the matrix permanent, which is the evil twin of the matrix determinant. No, seriously, because the matrix determinant is you take, all right, so determinant, as you probably remember, is you take all the permutations of the number of rows and columns, and you multiply the entries together. And you have all those pluses and minuses, right? So with the determinant, say for a 2 times 2 matrix, you do this whole AD minus BC thing, and then if it's a 3 by 3 matrix, then you have like a long row with like alternating pluses and minuses, and that actually makes things easier that there are the minuses because the determinant has a lot of nice linearity properties. The permanent doesn't have that -1. Other than that, it's the same, which might look nicer, right? This is I, right? So we're counting over the columns and multiplying the entries together. It looks nicer in the equation, but it's actually a lot harder to compute. It takes a lot of computational time to find the permanent. And it's not as nice as determinant. It doesn't have quite the properties. For this one, right? So it essentially, like, this is just going to count the number of ways you can pick one entry in each column and row so that all of those entries are 1, right? So one way to do it would be these 3. Another way to do it would be this, this, and this, right? Which actually is exactly the same as counting the number of perfect matchings, right? Because you're picking, by picking the row, you're picking the vertex here. By picking the column, you're picking a vertex here. And if they all have 1s, that's a perfect matching. If one of them has a 0, it's not. All right, so how many ways can we do it here? Two, that's right. Partly because, you have the same situation here as you did over there, right? Once you fix one, everything else falls down, like dominoes, But the 2 ways to do it is this one, and this one, or this one, and this one, right? You can't have 2 in one row, and you can't have 2 in one column. All right, so the permanent here is 2. Yep.
So if I have a graph with no edges, that's great for privacy, right? Because it suggests that no user exhibits any behavior. Is that the right way to interpret
So in this model, if you can't tell anything and any behavior could belong to any user, you just fill everything with edges.
I see. Okay.
Yeah. And, So you could say that, if you're observing a system, you can start with this complete graph, right? And then once you get new information, you delete edges, and that's your, corresponds to your new information.
So the reason I ask this is, so there is this sort of non-monotonicity as I go from 0 edges to whatever, and choose 2 edges or whatever, right? The maximum I can have. But you're saying that there's some threshold where I'm going to start with the maximum number of edges, and there's some threshold at which I stop removing them. I shouldn't go all the way down to 0 because then I have to start flipping the...
Well, so, you need at least n edges, right, if you have n users, because there must be some matching, right? Otherwise, you've gone too far, right? There's at least one underlying correct matching that has to exist. So you need some edges for that. But that could be as little as just n, it could just be a ladder like that.
Okay.
Other questions?
So the graph that corresponds to k-anonymity essentially will look like that, right?
Yeah, that's right. So the graph corresponds to, like,
So
here.
for every set,
Right.
you have all possible number of edges, and then they're all independent of each other.
That's right, exactly. So separate blobs, right? And these are complete. So it's K, K, K. That's what a complete bipartite graph usually is denoted in math, right? So and this is going to be complete. There's everything here. All right.
What if you don't know that the behaviors you're observing are coming from every user exactly once? Like, what if it could be that one of the behaviors, or 2 of the behaviors came from the same user and you never saw David?
Then you can probably do an intersection attack, right? And I think the way I would deal with that is merge those 2 behaviors, right? And delete edges accordingly, right?
Well,
so
you don't
take.
know that they came.
Okay.
It's just possible they came from the same user.
Yeah, maybe. Or you can probably put 2 copies to sort of a ghost copy of a user, and essentially that's going to make your job harder, right? So you might as well put in like a ghost copy of a user, and for every behavior, and see what you get out of that. Other questions? All right, so here's the main math building block of this whole thing. All right, it's called the Bregman theorem. Okay, so I want to have a lot of perfect matchings, right? So obviously, like, if I have n users and n behaviors, I'll have the most perfect matchings if there are edges everywhere, right?
But as you said, isn't that, is that enough?
Well, okay, so if we count edges here, right, there's going to be 9 edges here, 4 here, and 4 here, right? So that's 17 edges. And here's 16, 1, 2, 3, so that's 19 edges, right? So if you fix the number of edges and want to get to the maximum number of matchings, you have to go there, right? Because once you go to up to 19 edges, you can construct this one. Does that make sense? It's, essentially, you have some function, some function m, right? The number of matchings of little m, number of edges, right? This function is maximized with respect to little m in this model. I don't know. Is that?
So you define that as a good system? Like
Well, so there's,
you just want to show that k-anonymity matches that system.
So the reason that is a good system is, so essentially, just a lot of matchings by itself is not enough to say this is a good system, right? Because of this situation. But if I can show that k-anonymity has the most matchings, then k-anonymity doesn't have a problem that you would look, that the number of matchings by itself overlooks. All right, so there are 2 components to this logic, right? You want to have a lot of matchings, but then you might be leaving out some users. But k-anonymity doesn't leave out some users, so if that's the specific thing that has the most matchings, you're good. Yeah?
I suppose maybe what you want to formalize that as something like min entropy, where you look at for any user, you look at the minimum number of matchings.
That's right. And that's, well...
So there it would be 1.
That's right.
And there it would be 2. And k-anonymity says it's always at least k.
Mm-hmm. Yes.
Right? So
So
say your min
So-
min n, but it'll be like min entropy.
Yeah, so essentially, you can sort of, for every user, you sort of have to spread out probability among all the behaviors that that this user is adjacent to, right? And if it's not, like, if the maximum amount of probability is low, you're good. Was that legible? All right. Other questions? All right. Okay. This theorem is value on the permanent. It's actually, it used to be a conjecture for like 30 years, and then it got finally proved like in the 70s, I think. All right, so we have a matrix. So an n by n 0, 1 matrix, which is exactly the situation right here, with the sum of entries in ith row. I guess we can make it Ri. Then there's a bound on the permanent. The permanent of A is at most the product of the factorials of Ri to 1 over Ri. And that looks reasonably intimidating, but we're going to deconstruct it. All right. So if you have a collection of complete components like that, this is actually precisely this bound. All right, so if you have, all right, so this component gives you k factorial, this component gives you k factorial, and so on, right? And if you have n over k components, like notice that every vertex here has exactly k edges coming out of it, right? Which is the row sum for this vertex, right? So every row sum is k. So this bound happens to be, oh, sorry, this is probably too low. All right, I'm going to go over there. All right, so this bound here is you suddenly have k factorial 1 over k, and you multiply that n times. All right, but if you multiply that n times, you can just put that n in the exponent over there, right? N over k. But that's exactly the number of perfect matchings in the graph like that, right? Because you have n over k components. Every one of them contributes k factorial matchings individually, and they're independent of each other. So this is the max.
You have to deal with the case where k doesn't divide n evenly.
I have, yeah, so that's right. Yes, I do have a, it gets, there's a follow-up to this, right? But this is sort of the first most straightforward case, right? And it works. Excellent. So what do you have to do to make this a conclusive proof? Well, first of all, you have to deal with the case where n does not divide k. And then second, you have to deal with the case where it's not necessarily, you know, every user has exactly k edges, right? Because what if, you know, what about all those cases where, you know, those are not k, right? Maybe that's better. So here's the logic that I followed with that. To actually make that bound, where's the bound? The bound, as big as possible, you have to divide the degrees of the vertices as evenly as possible, right? So that's step one. Step two, achieve that maximum bound, or something that tends to that bound. And those two things together are actually conclusive. All right, so yes?
So in your example over there on your board, what if your budget was 15 edges?
That's right, yeah. So what I would do is I would take them out of here. And this is actually really cute. I'm told there are a few combinatorialists in the room, so you can probably, suppose you have a graph like this, and each vertex is adjacent to all vertices on the other side except the one on the same height, right? So it looks like this. Oh, sorry. No, that was actually okay. All right, so usually if every vertex was connected to every other vertex, you would be looking for the number of permutations, right? Because to this vertex, you can assign any of those. To this vertex, you can assign any of the remaining ones, and so on. What changes here?
You can't assign something to itself. So.
Exactly. All right, so here you have, so again, you have a bijection from 1 to n to 1 to n, right? But f of I is not I. Sorry?
Derangements.
Derangements, exactly. That's the word I was hoping to hear. All right, so these are called derangements. Do you remember how many of those there are?
It's like 1 over E.
Exactly, yep, precisely. So, all right. All right, so the number of derangements is looks like this. So of, say, let's call this, all right, let's just call it n. It's n factorial, right? So this would be just the number of permutations, but it has to be less than that. It's 1 over 2 factorial minus 1 over 3 factorial plus all of that, right? And that, you know, as n gets big, that tends to n factorial times 1 over e. So the limit as n tends to infinity of this is n factorial times 1 over e. Right? All right, so it turns out if you actually compare that to the Bregman bound, it tends to the same thing. And you use Stirling formula for that, you know, to sort of turn that into all the other stuff. I could probably show you how this works, right? So if you apply the Bregman bound to this, that's k factorial 1 plus 1 over k, right? If there wasn't this extra vertex and all of those were connected, it would just be k factorial. But this is what the bound is, right? Because it's n over k in the exponent. And so this is k factorial. And then use the Stirling formula, which is k over e 2 pi k. Right? This is approximation to what factorial is, and I just took it to 1 over k. Right? That's this whole thing. So, and that, you know, if you just divide this one thing by the other, you're left with the k 2 pi k, right, over 1 over k, sorry, and that actually turns to, oh, yeah, over n. And that actually tends to 1. Too much math? All right. So anyway, this means that what we can do when we don't have enough edges is create components that are complete, and then when we run out of edges, create components that look like that or somewhere in between. And that lets us, you know, have the number of matchings that is approximately the right number of matching, the maximum number of matchings. So bottom line is, you know, yeah, k-anonymity makes sense. You know, it's not just what we know how to do because we have ways to do it, like DC networks, but also, you know, you can make a math argument that you know, it might be better than overlapping anonymity sets. So there's actually, you could also talk about, like, what about if you would de-anonymize some users, how does the number of matchings get reduced? And it turns out that this is fairly resilient. And there's other constructions that are more resilient, but you start from a smaller number of matchings. So there's a trade-off, I guess. Cool. All right, thank you.